Hey everyone, in this video we're going to go over section 4.2, the mean value theorem. The mean value theorem is really going to get used later on as a tool to prove other theorems, but it's worth talking about in greater detail now. Unfortunately, the first step in talking about the mean value theorem is actually talking about Rolle's theorem. And what Rolle's theorem says is let f be a function that satisfies the following hypotheses. So let f be a function that satisfies the following hypotheses. So first, let f be continuous on the closed interval a to b. F is continuous on a to b. 2, f is differentiable on the open interval a to b. And f of a is equal to f of b. Perfect, so we're continuous on a closed interval, differentiable everywhere except for possibly at the endpoints, and these endpoints have the same y value. The result of Rolle's theorem says that then there is some number c with a less than c less than b. So we've got this number c somewhere in the open interval from a to b, such that f prime of c is equal to 0. Perfect. So Rolle's theorem says we've got this function that satisfies these three conditions. Continuous on a closed interval from a to b, differentiable on the open interval from a to b, and the y value of the two endpoints are equal to each other. Then it's saying that there's some number inside this interval where the derivative of this function f equals 0, or we have a horizontal tangent line. So we really have three possibilities for f. F can either be a constant function, so here's a, here's b, and if f is constant, then at every number between a and b, f prime of c is equal to 0, since it's a horizontal line. Our other option is that f isn't constant. Let's go over here. Our other option, like I said, is that f isn't constant. So f can start at some point, and it could say bend up. And since the two endpoints are the same, we know if f bends up at some point it has to bend back down. It's continuous. So what Rolle's theorem says is that there's some value c in the middle where there's a horizontal tangent line. F prime of c is equal to 0. The same is true if the function bends down. We start at some value of y, we bend down. Because we end at some value of y and we're continuous, we know we have to bend back up. Since we have to bend back up, there's a point where we have to change directions. And the point where we change directions has a slope of 0. C. So this is what Rolle's theorem is about. We either have constant functions, functions that bend up, or functions that bend down. But what Rolle's theorem is saying is that we are guaranteed at least one critical point between a and b if the endpoints are equal to each other. So, an example or an application of this theorem, let's say we had some particle whose position is given by some function of time. So we have their position or their displacement graphed against time. And so by Rolle's theorem, if we have a particle that starts and stops at the same location, well, that means that either the position didn't change, the particle never moved as time went forward, or the particle moved. If the particle moved, well, they moved away, and then if they ended at the same position, there's some point when they had to move back to where they started. So by Rolle's theorem, we know, and that pen is out of ink, by Rolle's theorem we know that there is at least one spot on this position function that has a horizontal tangent line. Well, s prime of t, or is the velocity of the function. So what it says is, if you start and stop in the same position, there's at least one value of t where your velocity equals to 0. So in order to change positions, you have to at least stop for a moment. But like I said earlier, the mean value theorem, and by extension Rolle's theorem, really get used in a theoretical sense. They get used to prove things about functions or get used to prove other theorems. So let's say, for example, we had, and this is example 2, x2, let's say we had the function x cubed plus x minus 1 is equal to 0. And what we're going to do is we're going to show that x cubed plus x minus 1 equals 0 has exactly one real root. So, how can we show that this thing has exactly one root? Well, the first step in showing that it has exactly one root is we have to show that it has at least one root. So we'll first show that it has at least one root, and the second thing we'll do is we will show that it can only have one root. So this is kind of our roadmap for this proof. So the first thing we want to do is show that it has a real root. Well, for one, if we take this polynomial, x cubed plus x minus 1, we can give it a name. Let's call this thing f of x. So, and let's talk about some values of f of x. In fact, let's talk about f of 0, which is 0 cubed plus 0 minus 1 is negative 1, and f of positive 1, which is equal to 1 cubed plus 1 minus 1, or a positive 1. So, if you look, as x varies from 0 to 1, y varies from negative 1 to positive 1. So by the intermediate value theorem, we know there exists a c between negative 1 and 1 such that f of c is equal to 0. We know polynomials are continuous everywhere. We know the y varies from negative 1 to 1, so there has to be some value of c that makes it so y is exactly equal to 0. Perfect. So this is all we need to do for part 1. We showed that this function has at least one root. Now we have to show that that there is only one root. In order to do that, we're going to use a proof by contradiction. Contradiction. And so, for a proof by contradiction, we are going to assume the opposite of what we want and prove that that has to be false. If the opposite is false, then that means the thing that we care about has to be true. So, in our proof by contradiction, I am going to assume f of x, or I'm going to assume x cubed plus x minus 1 equals 0 has more than 1 real root. Okay, so off of this assumption, that means that there has to exist some other c. So based off of this assumption, that means there is some, and I'm going to use the letter D, some D, some real number D such that f of D is equal to 0. Because after all, if this thing has more than one real root, then that means there's some real number that makes this statement true. Well, now look at what we have. We have this function that is equal to 0 when x is equal to c, and equal to 0 when f is equal to d. This function is continuous everywhere, and it's differentiable everywhere, so that means f of x is definitely continuous and differentiable on the interval from c to d. And like I said, our endpoints match. So this sets us up to use Rolle's theorem. By Rolle's theorem, we know there exists a, and we've already used C, we've already used D, I don't like to use E because that's a number, we've used F. I'm going to pick Z. There exists a real Z such that f prime of z is equal to 0. So by Rolle's theorem, this thing is continuous between c and d. I'm trying to find where I wrote c. Between c and d. It's differentiable between c and d. We know that because it's a polynomial. It's continuous and differentiable everywhere. And we have the function equals 0 at both these endpoints. By Rolle's theorem, that means that somewhere in between c and d, there exists a real z such that, and I should probably have c is less than z is less than d, such that the derivative is equal to 0 at z. But let's explore what f prime of x is. F prime of x is equal to 3x squared plus 1. And now, if you look, this function is a parabola. It's got positive orientation, it opens up, and it crosses the y-axis at the point 0, 1. We know, just geometrically, that there's nowhere that this function equals 0. It never crosses the x-axis. You could prove that to yourself by trying to set this thing equal to 0, and you get x squared is equal to negative 1/3. Well, we're only looking for real numbers here. So it's impossible for there to be this number z between c and d that makes it so the derivative is equal to 0, because it's impossible for this derivative ever to equal 0. If the thing we assumed is impossible, then the opposite has to be true. So that means this assumption that x cubed plus x minus 1 equals 0 has more than one real root is false. So we can say, thus, our assumption about there being more than one real root is false. Hence, x cubed plus x minus 1 equals 0 has exactly one real root. Perfect. So this is our proof. It used a little proof by contradiction. I'm not going to ask you to prove anything in this class, but it's good to, I think it's good to show you how mathematicians use these theorems. Moving on, we can actually go to the mean value theorem. So, the mean value theorem. So just like Rolle's theorem, we need well, the first two conditions of Rolle's theorem. One, f is continuous. Oops. F is continuous on the closed interval from a to b. And two, f is differentiable on the open interval from a to b. So what Rolle's theorem was about was if you have endpoints at the same height, then the function has to have a derivative equal to 0. If we generalize that a little bit, we get to this. So the mean value after those two conditions are met says then there's some number c such that a is less than c, which is less than b. I would say there's a c with a less than b less than c such that f prime of c is equal to f of b minus f of a all over b minus a. So what this is getting at is if I call this point A, and I'm going to call this point B, and I'm going to say that this is our f of A, and this is our, let's go up here. Alright, here is our f of B. So if we're continuous, it doesn't matter what this function does. I'm going to have it loop down and then go up. What the mean value theorem says is, and that pen is still empty, that this f of b minus f of a divided by b minus a, this is the slope of the line that connects the endpoints. This line has slope f of b minus f of a all over b minus a. What the mean value theorem says is there is some point on this slope where the derivative, the slope of the tangent line, is equal to the slope between the two endpoints. This is a value c right here, and this is f prime of c, which is equal to f of b minus f of a all over b minus a. Perfect. So no matter what this function does, and if I drew it wiggling up, I would have written over that. Once again, it doesn't matter the value of f of b and f of a. If f of b and f of a are equal to each other, then we just have Rolle's theorem. But what it's saying is we don't have to have them equal to each other. No matter what these two endpoints are, as long as the function is continuous, then you are guaranteed that at least one point in between that interval, the derivative is equal to the slope of the line connecting the endpoints. So this really gets used in theoretical applications, but we can see it in work. We're going to apply the mean value theorem. To f of x is equal to x cubed minus x on 0 to 2. Well, so first off we have to check that f of x is continuous and differentiable on the interval from 0 to 2, or continuous I should say on the closed interval from 0 to 2, and differentiable on the open interval from 0 to 2. But f of x is a polynomial, they're continuous everywhere and differentiable everywhere, so we meet those two conditions. Now we have to know the value of the endpoints. F of 0 is equal to 0 cubed minus 0 is 0, and f of 2 is equal to 2 cubed minus 2, or 8 minus 2, which is equal to 6. So, by the mean value theorem, we know there exists a c with 0 less than c less than 2 such that f prime of c is equal to, we need the slope between these two lines. Well, f prime of c is equal to f of 2 minus f of 0 all over 2 minus 0, or 6 minus 0 all over 2 minus 0, which is 3. So, by the mean value theorem, we are guaranteed this. So, let's find it. F prime of x is going to be equal to, taking the derivative, powers come down, 3x squared minus 1. And if we want to know where 3x squared minus 1 is equal to 3, all we have to do is solve for x. Add 1 to both sides, 3x squared is equal to 4, and then x squared is equal to 4 thirds, or x is equal to the square root of 4 thirds, which is 2 divided by the square root of 3. You should always rationalize your denominators. We're at 3, to give us 2 square roots of 3 divided by 3, which when we plug into a calculator or reference our notes, I didn't get a decimal. Let me plug this into a calculator real quick. So that worked out to be about 1.15. And something that I also realized was that when I took this square root, technically we would get a plus or minus and a plus or minus. So our answer, x would be plus or minus about 1.15. But what the mean value theorem says is it guarantees, and I should write a plus or minus right there, it guarantees that there is at least one root in that interval. There can be more than one root. There is at least one value of c in this interval that makes it so the slope of the tangent line is equal to the slope between the endpoints. We've found another one, and that's fine. All this theorem says is there is at least one in this interval. There can be more, but there is at least one in that interval. So just like with Rolle's theorem, let's talk about the mean value theorem in terms of particles. This doesn't have to be particles, this could even be your car. So, by the mean value theorem, let's say you drove 200 miles in 2 hours. Okay, so the distance that you traveled is continuous, and it's differentiable. It's differentiable because you know that you definitely have a velocity at every time in between 0 and 2. So by the mean value theorem, at some point during those 2 hours, you know that the derivative of your position or your velocity as a function of time is going to be equal to 200, the distance you traveled, all over the amount of time it took you to get there. So by the mean value theorem, we know if you drove 200 miles in 2 hours, well, that means there was at least one point, there was some specific time t where your velocity was equal to 100 miles per hour. So similar to Rolle's theorem, but a little bit different now. Instead of stopping, we know about velocities. So for our next example is example 5. So for example 5, we're going to say, suppose that f of 0 is equal to negative 3. And, sorry, I lost my spot. F prime of x is less than or equal to 5 for all values of x. For all values of x. How large can f of 2 be? So we have this function. We know that when x is equal to 0, its y value is negative 3. And we know that the derivative is less than or equal to 5, or the value of the derivative is less than or equal to 5 for any value of x. How large can f of 2 be? Well, so we're going to use the mean value theorem to show this. The mean value theorem says that we know that f prime of x is going to have to be equal to f of b minus f of a all over b minus a. And we know for this problem that has to be less than or equal to 5 because the derivative is less than or equal to 5. So we got to plug in some information here. So we're going to end at this point f of 2 minus f of 0 all over 2 minus 0 is still less than or equal to 5. Where we get f of 2 minus f of 0 is a negative 3. All divided by 2 is less than or equal to 5. Well, f of 2 minus negative 3 is the same as plus 3, and we can multiply a 2 on both sides to clear out the 2 in this denominator. F of 2 plus 3 now has to be less than or equal to 10. Subtracting 3, f of 2 has to be less than or equal to 7. So just by knowing information about an upper bound on the derivative and one specific value of the function, we're able to figure out the maximum value and upper bound for that function at a certain point. So the mean value theorem, like I said, really gets used for these theoretical sorts of proofs. It will be floating around in the background of a lot of future techniques. We won't necessarily always mention it by name, but it's definitely there. So let's go on to a theorem and then a corollary. So our theorem says if f prime of x is equal to 0 for all x between a and b, and by that I mean a less than x less than b. So if the derivative is equal to 0 for every x in between a and b, then f has to be constant. Then f has to be constant on a to b. So this is going to be an application of the mean value theorem. We know that f prime of x is going to be equal to f of b minus f of a all over b minus a. And if the derivative is always equal to 0, then that means f of b and f of a have to have the same value for every a and b. So by the mean value theorem, this checks out. Our corollary is if f prime of x is equal to g prime of x for all x between A and B, I crossed my B, between A and B, then f minus g is constant on A to B, and f is equal to g plus some constant, where c is a constant, plus c where c is a constant. So this result we're actually going to get entirely from our theorem. So if f prime of x is equal to g prime of x, well, that would imply that f prime of x minus g prime of x is equal to 0 for all values of x. Or the derivative of f minus the derivative of g is also the same as the derivative with regards to x of f of x minus g of x is equal to 0. I probably should have stuck with this notation, so let me rewrite this as saying that f of x minus g of x prime is equal to 0. So these two derivatives are equal. That means their difference has to be equal to 0. If they're equal for all values of x, that means their derivative has to be equal to 0 for all values of x. And what it says is f has to be constant. That means f of x minus g of x has to be constant or equal to some value of c at every value. What that means is that f of x is equal to g of x plus some c. So let me say all that again. So if f prime of x is equal to g prime of x, well, that means we could subtract g prime of x from both sides. We could have subtracted f of x from both sides, or f prime of x, I'm sorry. We chose to subtract a g prime of x from both sides, and we get that f prime of x, minus g prime of x is equal to 0. Well, derivatives distribute over subtraction, so f prime of x minus g prime of x is the same as the derivative of f of x minus g of x is equal to 0. Perfect. So we're up here at our theorem. If f prime of x, if the derivative of some function is equal to 0 for all values of x on the interval, on some interval, then the function has to be constant. We know that this function, its derivative is equal to 0 at every value of x between a and b. That means that this function is constant on a to b, and f is equal to g plus c. So by this result, we know that f has to be constant, or our function has to be constant, which proves this part, and some algebra gets us here. So this is our corollary and our theorem. So for our final example. For our final example, we want to prove the following identity. Prove that the tan inverse of an x plus the cotangent inverse of an x is always equal to pi halves. So, prove that. Let's prove this identity. So, in order to do so, we're actually just going to use this theorem. So we have this tan inverse of x plus cotangent inverse of x. Let's call this thing a function. Let's say we have f of x is the tan inverse of an x plus the cotangent inverse of an x. And now let's talk about the derivative. F prime of x is going to be 1 over 1 plus x squared plus a negative 1 over 1 plus x squared, which is equal to 0 for any value of x. So we have the derivative of this function is equal to 0 for all x between a and b. Well, right here, f prime of x is equal to 0 for all real numbers. Perfect. So what it says is then f has to be constant for all real numbers. Then f of x is constant for all real numbers. Well, if f of x is constant for all real numbers, let's figure out what f of x is equal to. Let's figure out what the tangent, or let's figure out what f of 1 is. Well, that's going to be equal to the tan inverse of 1 plus the cotangent inverse of 1. Well, the tan inverse of 1 is pi fourth. That's where sine is equal to cosine. And similarly, cotangent of 1 is where sine is equal to cosine, which is also equal to pi fourths. This shows that f of 1 is equal to pi halves. And because this derivative is always equal to 0, we know f of x has to equal pi halves for all x. Or, said in the context of this problem, that means the tan inverse of an x plus the cotangent inverse of an x is equal to pi halves for every value of x. So that really wraps up this section. We went, like I said, we went over Rolle's theorem. Rolle's theorem is really gets used as a stepping stone to prove the mean value theorem. Any result you get from Rolle's theorem, you can also get from the mean value theorem. So that one gets used more often, more frequently, I would say. And the mean value theorem usually gets used in a more theoretical context. You use it to prove the existence of something. There's some problems you guys are gonna do for your homework, like the one where we found it said apply the mean value theorem to x cubed minus x over a certain interval. That's really just kind of proving to you guys that the mean value theorem always works. You guys can find these numbers. And with that example, the x cubed minus x on the interval from 0 to 2. Remember that we actually got x being equal to plus or minus about 1.15, and we disregarded the negative sign because we only care about the value that lands in that interval, because our theorem guarantees a number in that interval. It doesn't say that other locations don't exist. It just guarantees the existence of at least one thing. For homework, go off and do 5, 7, 11, 13, 19, 21, and 25. And send me an email if you guys have any questions with that. Have a nice day. Bye-bye.